Our next speaker is Pradipta Pathak, and he will be talking about holomorphic factorization at the quantum horizon.
Yeah, so good morning to everyone. I would first like to thank the organizers for this symposium and also for providing me an opportunity to speak. So I will be speaking about this recent paper that appeared with Chetan, this paper, and I will be also talking about the main results from this paper. Okay, so let's go into this. So basically, the wave equation, I will be motivating my talk from the language of wave equations. The wave equations around black holes capture bulk perturbations. Now, since gravity is a holographic theory, the background black hole together with these perturbations can be viewed as the bulk representation of the black hole microstate sliver in the CFT. These states should therefore be responsible for the entropy of the black hole in the microcanonical ensemble. However, there are immediate obstructions to this point of view. A potential, let me not go into what are the immediate obstructions, but the potential resolution that was advocated in these papers was that to introduce a stretched horizon, basically a boundary condition which cuts off the space-time before a few Planck lengths away from the physical horizon of the black hole. This Planck length is in quotation marks because it shouldn't be taken so literally. It is just a measure of the Planckian or the stringy length scale that is present in the problem. Okay, so with that, stretched horizon is basically a finite n effect. That is why we are viewing it as a quantum horizon. One crucial observation that was obtained from this paper was that one shouldn't be working with the stretched horizon vacuum because the stress energy tensor, the wave of the stress energy tensor is negative, is divergent as you go close to the stretched horizon. That is why we are working with the excitations at a sliver of energy closer to the mass of the black hole. Or in our case, the ensemble is defined by the temperature of the black hole, as we will see. The normal modes of these bulk fluctuations constructed with the boundary condition precisely produces for us the entropy, temperature, as well as the Hartle-Locking correlator as one goes to the n going to infinity limit. These observations, together with many other observations from these couple of papers, was that normal modes of wave equations are approximate proxies for the UV complete spectrum that are responsible for the black hole thermodynamics. This also raises a natural possibility that the simplicity of the black hole thermodynamics is reflected in some manner in the black hole wave equations, which even for very complicated metrics. For example, one can check the metric that Sweat-Chiom developed for the 5D black holes. Okay, so the purview that we take in our work is that this simplicity of the wave equations is not merely a curiosity, but is an expected feature to carry on this normal mode wave equation business into the general class of black holes. Okay, so the black holes that we consider, the higher dimensional black holes that we consider are away from extremality and supersymmetry that is generally considered for the BPS type systems. But the systems are tractable, and thanks to the simple structures of their wave equation. So the first persons to guess this hidden conformal symmetry in the higher dimensional black holes were the Sweat-Chiom and the Castro-Maloney-Strominger guys. So what they did was they discovered that there is this type of symmetry around the wave equations which reduces then to the hypergeometric forms. It was known as the near region. It was known as the near region limit. But the problem was what they did was, in the CFT we know that there is a relation between the SL and the TL via Cardy formula. So by this symmetry structure, the TL and TR that appeared in the conformal coordinates are naturally the temperatures of the dual CFT, and by the asymptotic symmetry calculations in the extremal limits of these black holes, we knew that the central charge was 12J. By that, they were able to precisely produce the black hole thermodynamics and the entropy. What we do is a variant of that limit, because that is the horizon skimming limit. These wave equations, this limit retains the left-right temperature concept as well as this conformal symmetry concept. The key feature that we find with our limit, and this was not true in the previous limit, was that the natural low-lying normal modes in this limit can also carry the black hole entropy. So the statistical mechanics of of these low-lying normal modes have the structure of holomorphically factorized 2D CFT, again thanks to the hidden conformal symmetry. So the left and right temperatures together with the central charge determines for us the thermodynamics completely. The inputs that we use in our calculation is the number of species excited at the stretched horizon, the stretched horizon location which is remarked by this Z0, and the angular quantum number cut off L cut, which can be combined into the freedom in a single real parameter. This was not realized in the previous works, but this parameter has direct interpretation as the normal mode central charge of the factorized CFT. So correctly reproducing the detailed thermodynamics of these black holes means the central charge of the normal mode quantum gas is precisely the Kerr CFT central charge. So we view this as the refined version of the Toofian quantum gas. Like what Toof did was, he introduced a stretched horizon type of cutoff, and he was able to get a area scaling and not the precise matching of the entropy. Our refined version of this system can be made precisely consistent with the thermodynamics of very general class of black holes. Natural holomorphic factorization that emerges in these large classes of black holes plays a crucial role in this business. So let us discuss what this holomorphic factorization and the horizon skimming limit means. So I will first set the stage by working with the simplest background, that is the BTC background. Okay. The field equation for the massless probe scalar in this, what we will do is, you can have a massless probe scalar in this background, and with the stretched horizon boundary condition you can write a wave equation. We will rewrite that equation by exploiting this symmetry in the background. For this purpose we adopt conformal coordinates, that is this w plus w minus and y. The crucial fact is that this TL and TR have interpretation as the physical left and right temperatures via Rindler type argument. This goes as follows, because this w plus w minus are the analog of Minkowski coordinates, and this phi and this type of coordinate is a Rindler type of coordinate. That is why these temperatures are interpreted as, these are natural temperatures. Before going further, let me just say that the z coordinate that we work with, in this z coordinate the inner and outer horizons correspond to z going to minus infinity and z equal to 0 respectively, and z equal to 1 corresponds to the ADS boundary, or in asymptotically flat black holes the asymptotic boundary. With this conformal coordinates we can construct a quadratic Casimir that gives the wave equation in terms of this ansatz as this. So this is the structure that we are calling as the holomorphically factorized equation, because it has natural presence of TL, TR and KL, KR. But the natural question that arises is, in the BTC case we could have always written it in the naturally occurring parameters, that is the R plus, R minus and L. So why are we writing this form of the wave equation? This is because the motivation is that this form will arise universally in the horizon skimming limits of the higher dimensional black holes. I will discuss what horizon skimming limit means in a while. So, and since this is a universal structure, we would like to develop the normal modes of this system and also develop the statistical mechanics for that. For that, we demand a normalizability at the boundary and Dirichlet at the stretched horizon, and we get the analytic low-lying spectrum for omega tilde. That is the co-rotating mode, because the black hole is, because we are working with a rotating BTC background. This has a linear growth along the principal quantum number n and has weak angular quantum number m dependence for at least the lower parts of the lower parts of m's. The factorization basically means that the wave equation has a natural emergence of TL-TR structure, right? So what happens is that because there is a left moving and right moving thing because of this SL2R symmetry, you can always do the statistical mechanics calculation in terms of the left and right guys separately. Okay. So we have already obtained this spectrum in the previous work, but so directly borrowing that result from there and ignoring the weak M dependence, which is all what we will need for this talk, will give us a degenerate type of spectrum where n belongs to the positive integers. The last equality is just a tool to be useful for the statistical mechanics calculations. Now you see that this spectrum is a strictly degenerate spectrum in M, because omega tilde has dependence both on n and m. Therefore, MCUT is we view MCUT as one of the UV inputs, and it will make sure that the partition function and the entropy are well defined. Also, as I just said, that the left and right moving structure of that equation naturally suggests that we compute the statistical mechanics in a holomorphically factorized manner. So with that and these conditions, that NS, MCUT and Z0, one thing is that we work with the same MCUT and Z0 for all the species of fields, but even if you change this condition to different MCUT and Z0, nothing will change physically. Starting with the partition function of the right movers and the left movers, we get this relation. Now this relation is a famous relation known as, the Cardy relation in the 2D CFTs. So this quantity, that's an NS MCUT by omega naught prime. Omega naught prime contains information about Z0, the stress horizon location. We get the normal mode central charge, which can be read off like this. Now this structure ensures that our black hole is dual to the dual CFT at the temperatures TL and TR. That is why, and with that temperatures, and if you identify this normal mode central charge to be the Brown-Hinox central charge that we generally know, it reproduces for you the correct BTZ entropy. So this is how we believe it to be this structure, we believe it to be the mechanical origin for the central charge. Okay, now let's go to the higher dimensional cases. The first higher dimensional cases that we consider is Kerr-Newman, and it is characterized by mass m, angular momentum j, and charge q. These are the angular equation, and this is the radial equation. Now this function is an explicitly known function. I have just written it in this form to save space, with the massless scalar ansatz as this. Okay. Now the problem is that due to the presence of this extra term, solving this wave equation exactly is not analytically very useful. So what we do is we go to a horizon skimming limit. That is, we go very near to the horizon. This inequality I'll explain in a minute. In the z coordinates, it corresponds to this, and this is the technical fact. Okay. So you see that the outer horizon radius sets the biggest scale among the black hole parameters, and that is why any quantity that is composed of this type of any dimensionless quantity that is made out of this omega tilde in this manner will always go to 0. This comes because the spectrum contained a log term. That log term basically provides for us this hierarchy. So with that, working with the stretched horizon boundary condition, we can almost turn this radial equation into the holomorphic factorization equation, but with an extra term from the second line. Now there are some technical details involved in this, so let me not go into that, but the claim is that the two key properties that allowed us to match the thermodynamics of the BTZ normal modes are still present in the system despite the presence of this extra term. That is, the spectrum having weak dependence on the angular directions, and the entropy can be explained by retaining only modes up to some angular momentum cutoff L cut in this regime. The argument for this goes as follows, that this extra term does not affect the magnitude of the normal modes, nor the fact that there is an approximate degeneracy. This statement should be taken with some modulus of minor caveats, but this doesn't matter. Now, for testing the argument, we should be checking it in all the possible values of m's and l's, but there are some technical difficulties in doing that. So we have solved it in the two extreme cases. That is, the first case is when this term is vanishing. This can be, if you can check that when this term is vanishing, this equation can just be translated into the TLTR, KLKR language by this identification. The second case is when m is equal to 0. The second case with m equal to 0 has already been solved in the previous work. So the modes we find, in these two extremes, the mode we find and degenerate to a first approximation. This is all what we will need to generate our thermodynamics. We can therefore argue that they behave likewise in the intermediate cases. Now with the spectrum that we saw, we can go on to compute its partition function. Since this is a 3+1D black hole, the states are labeled by n, l and m, and for any form of the car pile that we always have m between -L to L. So with the analog of the M cut being L cut here, we get this relation, and again doing the same step, we reproduce the correct left and right entropy. Now the last higher dimensional case that we will discuss is the Sweaty-Chiom case. So the Sweaty-Chiom black holes are basically most general black holes of the low energy effective action for the type 2 or heterotic string theory, toroidally compactified down to 5 dimensions. Now they are characterized by mass m, 2 independent angular momenta and 3 u1 charges. The angular and radial equation in this background has a similar form as Kerr-Newman, hence the discussion from here proceeds analogously, so I will not repeat it here. But one thing that makes this higher dimensional wave equation slightly more interesting is that we have two azimuthal angles in this, that is phi and psi. So we have two azimuthal quantum numbers m phi and m psi, whereas the 3 plus 1D Kerr-Newman case came naturally with one azimuthal angle. The problem in this is that how do you identify the TL and TR if you have these two as separate? The solution is that we find that in any direction of the phi psi plane, this will be a well defined definition of the left and right temperatures as well as the left and right symmetric central charge. This point is very natural from holomorphic factorization perspective, but historically only special case has been considered in the literature, that is the Myers-Perry case. I will discuss in a bit. Now along any direction in this phi psi plane, the spectrum remains identical and degenerate because of this point. Now one can check that along all the directions the spectrum will remain identical. It is a very trivial check. So the only difference from we can compute the partition function for this normal mode quantum gas, that is we have an S3 instead of S2, so the states will be labeled by this and this. So finally we get this expression between SLR and TLR. The case with all the QIs turned off is usually referred. So this is now we want to go to a direction to test this, to reproduce the results that has been produced in history. So in particular case, to find the evidence of Kerr CFT, the M psi equal to 0 wave equation has already been discussed in this. Looking along MR equal to ML, so M psi is equal to 0 means MR is equal to ML, looking in the MR equal to ML or the M phi direction in the plane. Hence we have the left and right temperatures, and finally we identify the Kerr CFT central charge as like this. So this note this scaling on top of the L cut. This is going to be important because the normal mode central charge has the angular quantum number. Normal mode central charge is proportional to the angular quantum numbers L cut. Now why is this important is because the L cut is having a power of 2 and in the Kerr-Newman L cut and power of 3 in this dimension. So this is a codimension. So this is a codimension 2 type of thing. This is happening because the modes are degenerate in the angular direction, and this is what is giving rise to the entropy. And this is automatically and this is true because the angular momentum modes are carrying the entropy. So this is completely automatic in our setup because the area scaling of J in central charge is captured by the power of L cut. That is normal mode central charge. So we view this type of relation as the mechanical origin for the central charge that has been known in the literature for long. So okay, so let me just thank and invite questions.
Thank you, Pradipta, for a very clear talk and finishing on time. So questions for him.
When you generalize the theory for fifth dimension, then you told there are two angular momenta. But these angular momenta really, because I am in PhD first year.
No, basically it just comes from the metric. So basically, if I can say, okay. So if you just write down the metric for the 5 dimensions, you will get there are two angular directions like phi and psi. So you will get J phi and J psi. So J phi and J psi, J phi plus J psi and J phi minus J psi are basically what JR and JL are.
Okay, and what is 3 plus 1 dimension? It is 4 dimension?
4 dimensions, yes.
So for 4 dimension, the state should be represented by 4 quantum numbers. But
no, 3 quantum numbers. You recall the hydrogen atom problem?
Yes, so it is a 3 dimension problem. So we need three independent quantum numbers, and
But it is on the S2, right? The partition function that is getting computed. The partition function that is getting computed is in the. So what do you mean? Like we have three quantum numbers, like in the hydrogen atom problem.
yes, but that is the case for 3 dimension, and you told there is the case for 4 dimension. So there should be 4 quantum numbers to state a state.
No, I said. No, wait.
Okay.
Yeah.
Okay.
Yeah. Thanks.
Okay, so there, next question.
Can you speak louder?
So that L cut, I mean, so you are putting a cutoff on that angular momentum quantum number. So how do you decide that?
No, basically, see, the first impression is that, like, if you obtain the full spectrum, you will get a log of m there. Okay, if you compute the full spectrum from here, the analytic low-lying spectrum, you will have an m in here. But the thing is that this this is a quite. I will just draw the spectrum. Just a minute. The thing is that this is the full analytic low-lying spectrum, but the entropy is getting contributions only in small region, where the spectrum is quasi-degenerate, and you will find that as you increase this log of Z0, the spectrum gets flatter and flatter. So this we have checked for many different cases, for many different cutoffs. So that is why we are working with a degenerate spectrum. And since we are working with a degenerate spectrum, it is natural to put a cutoff on the angular quantum numbers. This we view as one of the UV inputs. Yeah, but one thing is that, one future direction is that, since this is weakly rising
So,
in.
sorry, may I ask for a clarification that I couldn't understand the full flow of the calculations, but do you show that if you put a cutoff and the rest of the contributions are getting somehow suppressed or something?
No, but the contributions are not getting suppressed.
L cut. How L cut should depend on the other parameters of the black hole or something. Yeah.
L cut doesn't actually depend on the other parameters, right? Because L cut is, there are 3 independent UV inputs that we are using in our problem. That is, L cut is an independent UV input.
Okay.
L cut doesn't depend on other parameters. One direction is that basically this since the spectrum is weakly rising, the natural expectation is that the spectrum should have a natural cutoff on the end to compute this entropy. But the thing is that one has to go to the second quantized spectrum for this, and there are only numerical control on that regime for very high m's. So one has to be careful in making those statements.
Okay.
So thanks again, Pradipta.
Thank you.